All right, welcome back. So in the last video, we covered the validation set approach. That's where we randomly sample a training set and a validation set from our available data. If you haven't seen that video yet, I recommend you watch that first. The link is in the description below. Today, we are upgrading. Cross-validation is a much more robust method. Instead of just one split, it repeatedly splits the data into multiple training and testing sets. It gives us a more reliable estimate by averaging the results across all these splits. The goal here is to ensure the model isn't just memorizing the training data, but is actually performing well on unseen data. All right, let's first cover k-fold cross-validation. Here, the data is split into k equally sized folds. So imagine we have our data set here with k equals 5. We train the model on k-1 folds, and we test it on the remaining 1. And we repeat this process k times. Every single fold gets a turn serving as the test set. We then calculate the MSE for each fold. The final performance metric is just the average of the metrics from each iteration. Simple, right? Now, what if we took this to the extreme? Type number 2, leave one out cross-validation, or LOOCV. Sorry, I was glitching there for a second. LOOCV. This is actually just a simpler case of k-fold cross-validation, where k is equal to the number of observations n, so each fold is one observation. A quick note about the bias variance trade-off. Recall the U-shaped curve from the bias variance trade-off video, where the minimum test MSE is achieved at the minimum point of the curve, balancing bias and variance. When assessing fit for cross-validation, we are not always interested in the actual numerical value of the MSE. Sometimes, we just want to find the corresponding flexibility level that yields the lowest test error. This is because even though different cross-validation methods might give you different curves, they generally follow the same pattern. They both successfully point to the correct flexibility level that corresponds to the smallest test MSE. All right, everybody, example time with visuals. Let's take a look at a dataset and perform threefold cross-validation. We have 6 observations here. We'll split them into 3 equal folds, with each fold containing 2 observations. Since k equals 3, we'll run the algorithm 3 times, with each fold serving as the test set once. In iteration 1, fold 1 is the test set, shown in red. Folds 2 and 3 make up the training set, shown in green. We fit a model on the green points and get the equation 1.9x minus 0.8. We calculate predictions for our test points, x equals 1 and x equals 2, resulting in y hat 1 equals 1.1 and y hat 2 equals 3.0. We then calculate the mean squared error by taking the sum of squared errors and dividing by the number of observations. This gets us 0.405, and we'll just store that here for safekeeping. In iteration 2, fold 2 becomes the test set. We train on folds 1 and 3. We get our new equation, y hat equals 1.76x minus 0.18. The approximation is due to rounding. We plug in our test x values for observations 3 and 4 to get our estimates of 5.12 and 6.88. We calculate the MSE, which comes out to be around 0.014. Iteration 3, validating on fold 3. We use our simple regression line to predict 8.5 and 10.2. This results in an MSE of 0.445. Finally, we average our 3 MSE values to get an estimated test error of 0.288. In this example, we used simple linear regression to fit the model. But what if we used another model, such as a polynomial fit, or a decision tree, or ridge regression? Each fit would give us a different average MSE. So one of the main benefits of cross-validation is that it allows us to assess the fit of different models in a more robust way than just using a single split. If we run this process multiple times using different models, we can compare the MSEs and select the model that generalizes best to new data. So far, we've covered cross-validation for assessing different models. We know it's great for that. But wait, there's more! Cross-validation is more than a one-trick pony. It's also great for selecting hyperparameters. But first, what on earth is a hyperparameter? A hyperparameter is an assumption you set before the learning process begins. The model can't learn these settings from the data on its own. Let's go through a list to demonstrate just how foundational cross-validation is to different statistical models. All of these are on the exam syllabus. We'll cover some of the specifics in later videos, but check out how often this pops up. In boosting, we use it to decide how many trees to grow sequentially. In pruning, it helps us select the subtree that minimizes test error. Principal components regression? You guessed it, it helps choose the number of components. And for shrinkage methods like ridge regression and the lasso, it's used to find our favorite tuning parameter, lambda. Even in k nearest neighbors, it tells us which k is a-okay. Before we end the video, let's quickly go through the advantages of cross-validation over other metrics for model selection. We have these other metrics: Mallow's CP, a Akaike information criterion, Bayesian information criterion, and adjusted R-squared, which are all on the syllabus. One advantage of validation approaches over these metrics is that it provides a direct estimate of the test error with fewer assumptions about the underlying model. And given modern advancements in technology, it's more feasible to run cross-validation than before, making it an even more attractive approach for model selection. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.